Welcome to the Houdini 16 Masterclass for Flip Fluid Simulation. In this masterclass, we'll talk about several features we've added to the new version of Houdini and go through some examples of how you might want to use them and some things to take into consideration when using them. The features that we've added are this idea of a waterline, which gives you a semi-open boundary at the volume limits. So originally, you had either a closed or an open boundary, and fluid could either flow out of the boundary or it would be completely blocked as if it was a glass wall. We've now allowed the ability for you to set a line at which things can exit gracefully, and below that line, the fluid will be contained at that boundary. We've extended this further with a boundary layer approach, which allows us to not only have these semi-open boundaries, but now we can assign velocity at these boundaries to get inflow and outflow velocities, which are quite useful for much larger simulations like oceans, where we only want to simulate a small region, but we have the velocity of the ocean that we can bring in at these walls. It also allows us to maintain the appropriate surface geometry so that we can have particles flow into the simulation if we want to have something like waves, for example. And this plays really well into the oceans. Although that's a different masterclass, it's important to mention that some of these improvements for the flipped fluid simulation are quite useful for oceans. In this masterclass, we use the boundary layer approach to construct a river and control its inflow and outflow velocities, as well as maintaining the water level of the river throughout the simulation. We can take this even further and up-res a section of the river by applying the pre-baked low-res simulation at the boundary layer. With this approach, our up-resed river matches the flow rate and water level of the low-res simulation with even richer detail. We've also added new effects like surface tension, for example, that allow you to achieve crown splashes or dripping faucets, and this implementation for surface tension extends to what's a really interesting tool, our suction fluid tool that we've added in our particle fluid shelf that can direct fluids towards an object and can be moved around in an animated object. And we'll show some interesting examples there. Finally, we've made some improvements to our viscosity solver that gives artists more direct control on how fluid flows when in contact with the collision. Typically, viscous fluid just sticks at the collision, and we've allowed you to have more control over that, where you can control how much it slips at the collision. And that allows us to also create some interesting effects as well. All right, so let's dive right into the waterline example here. So I've created a pool that is just basically from the flip tank with a few changes. I've added an emitter from the emit particle fluid shelf tool and give it some downward velocity to create a big splash. And indeed, we get this nice big splash that eventually comes in contact with our volume limits. We see that we get some wash up at the glass wall here, right at the volume limits. It's not super obvious, but you can kind of tell that there's a boundary there. It becomes more obvious as the simulation continues because we start getting reflections back into the main part of the simulation and then back out against the wall. So we get ripples that show up along the wall here that travel. And then this becomes really obvious that we're getting a lot of rock back and forth from our initial splash. Now, if the scene we want to capture is inside a glass wall, inside of an aquarium, for example, well, that's great. This looks good. This is nice. But it's possible that we want to maybe capture this type of splash in a much larger pool, and we don't want that type of wash up along the walls. Now, we could extend the boundaries to have a much bigger pool, but that just means the ripples have longer to travel, but they'll eventually come back in. So we'd have to make the pool big enough that the reflections never get back into the main part of the scene by the time our scene is finished. But that can be quite expensive. You might not want to simulate a pool that is that big. So we've added a feature to handle that in the flip solver in the flip solver node under the volume motion tab, volume limits tab inside of that, called waterline. And this converts our closed boundaries into partially open boundaries. So if we visualize the plane here, anything above this plane along the boundaries is considered open, so the fluid can freely leave. Anything below this is considered closed, and the fluid is contained. So I want to move this down to be at the same level as my fluid. There we go. and I want the direction to be pointing upwards. I can change the direction and angle this plane if I want to, and again, anything above the plane is considered open and can leave, and anything below is considered closed and is contained. But for this example, we'll just keep it flat. So let's run this again. We get our big splash. Okay, that's great. And it gets right to the limit, and as it does, you see that particles start disappearing. They're not keeping along the glass wall like before. And we're also not seeing a huge amount of water forming up along the wall because it's allowed to freely exit the simulation now. You see some of the particles are leaving and the level is dropping down. And when we get this washback, it's not nearly as energetic as before. If you recall, it washed all the way up the walls last time. This is substantially attenuated. We do not have the same reflection issues that we had in the previous example. So this does really significantly reduce the amount of reflections we get inside the simulation. And it's a lot easier to mesh this with a extended pool and make this look as if it's part of a bigger simulation or a bigger pool or whatever you're trying to create. Whereas you wouldn't have been able to achieve this before using just the volume limits. It would have required a much more complicated setup with maybe collision volumes and other type of geometry. Okay, that's great, but we notice that there is some volume loss. It's not quite, it's not quite at the water level. There's certainly dips here. It does look like we've lost some volume. Certainly in smaller simulations, this becomes really apparently obvious. And we can address this using the boundary layer option. So the boundary layer is a much more advanced version of waterline. If we turn this on, we get several options. For starters, we have a padding control. So around the volume limits, how thick do we want our boundary layer to be? In this case, it's 1 meter. It can be set to whatever you need to. Just remember to keep in mind the voxel size. So for example, what is your particle separation and grid scale? And is your boundary layer actually big enough to do anything? And inside of that boundary layer, we also have surface volume and velocity volume. Now, this is important. Before with waterline, things would hit the glass wall, the volume limits, and it would either be able to leave or it would have to stop because it's hitting a collision. Now, with velocity volume, we can change that. We can have the velocity create inflow or outflow velocities. So we can actually have scripted velocity at the volume limits where it wasn't possible to do that before. And that's strictly enforced, that the velocity at that has to be conforming to whatever is input through the velocity volume. The surface volume allows us to control the geometry in the boundary layer padding. So for example, we don't have a surface volume connected here, but we have waterline. So this says anything below the waterline is going to constantly be reseated within the padding. Anything above the waterline is going to be completely deleted because it shouldn't be there. This is trying to maintain the boundary geometry to match some maybe extended scene that you want to create. Now this is used heavily in the ocean tools, but that's going to be discussed in a different masterclass. So for the moment, we're not going to wire anything in here. And if you don't have anything connected, it defaults to use the waterline. And so the waterline takes control of the boundary layer if there's no surface volume connected. So we run this splash. We notice that we actually lose particles quite a bit sooner. And like I said before, anything that's above the surface in the boundary layer gets deleted, and any empty space that's below the surface in the boundary layer just gets reseated. So we can maintain the water level. In this case, it seems a bit abrupt, but this would be the same sort of thing you'd see at the glass wall with a normal water line. But this allows water to actually flow back into the simulation, because if there is if there is a dip, which you see along here, the actual boundary layer can allow particles to flow back into the simulation. So we can always maintain the water level by having this boundary layer set up. So let's take a look at that again. Let's watch that. Notice how we don't really see a whole lot of reflections going on here like we did before, because the boundary layer takes in some of the velocity that comes out of our motion here. And when there's washback, where we notice that we were sort of losing volume, the boundary layer supplies the particles necessary to wash back into the overall simulation, and it remains quite flat. We don't have the same problems that we had before. Now there will be some seam issues that go on, like it's obvious that there's a boundary layer here because it's quite abrupt. But that's something that's going to require, adjusting in your particular scene. But what's really important to take away here is that as the energy of the simulation goes out into the boundary layer absorbs some of that. It changes color, it gets some of the velocity, and then as there is some backfill here, the particles are allowed to rush back into the simulation. You would sort of expect this in a much bigger pool that you'd get wash in and out if this was much bigger. So we do get the nice big middle splash we wanted, but we don't get a whole lot of the reflection and washback that we would have gotten if we didn't have any of this at all. And we don't lose the volume that we would have lost if we had the waterline only activated and without the boundary layer. So these are pretty useful tools for maintaining this sort of continuous tank type of appearance. And this can be used for much more complicated things like getting an inflow, outflow velocities from oceans and being able to maintain the overall ocean volume and appearance. But again, that's discussed in a different masterclass. But we can use this to drive rivers and even resim rivers. Okay, now that we've seen that the boundary layer is useful for preventing reflections, let's move on to something more complicated. The boundary layer is much more advanced. We can control the boundary geometry that is not just the waterline, and we can control boundary velocity that's not just zero. We can actually provide volumes that prescribe how the velocity at the boundary should behave. So let's dive into our river geometry here first and just see what we're looking at. Oh, I'm going to turn off the particles. Right. So pretty simple. I just added some noise to a couple boxes and nothing fancy. Turn that into a VDB through the collision source, and so we have a volume here. We want to create the actual geometry itself for the fluid. So if we have a box that sits sort of inside the river, and turn that into a volume, and then do a simple Boolean on that. A volume Boolean, that is, we get a volume that looks like what the water should be along the stretch of the river. Okay, so we can use this null here and wire it into our flip solver to initialize all the particles and start the river, but we want to maintain the river level over time. And the boundary layer allows us to do that because we can prescribe what the surface should be at the boundary layer, and we can prescribe what the velocity should be, again, at the boundary layer through those source and velocity volume connections. So on this side, we create some velocity volume by creating a vector. We give it some initial flow rate, so 3 meters per second, and we make sure that it matches up to the size of the box, and then we have some velocity that we can pass through. Okay, let's just this flag to display. Right. So let's dive into our actual flip solver. So instead of having our waterline turned on as before, we have that completely off. We have our use boundary layer. We've made the padding quite a bit bigger because this is a substantially bigger simulation than the last example. So we have 4 voxels in, 4 meters in, and on both sides. And we only need the X in this case because this is along the X axis. We don't care about the Z padding because there's no inflow, outflow on the Z. And there's also no inflow outflow on the y's either. So yes, we can set 4 for the x-axis limits, and we can leave everything else out. All right, as I said before, if we want to maintain the overall level of the fluid, we want to wire in our geometries at the boundary. So what we want to sort of maintain over time. Now, this is not animated at all. This is just a static box, but you can add animated surfaces that get wired in here, and we will do that later. Also, we've wired in our velocity, so now at the wall and within this padding, we are going to apply whatever velocity we bring in here. So in this case, it's just a straight 3 meters per second flow in the x direction. And finally, we have this apply boundary tab, which we didn't look at in the waterline example because there was no velocity to apply. It was just a 0 velocity because we were assuming just a static pool in the sort of the infinite space outside of it. So if you have the apply boundaries activated, then when a particle gets reseated in the boundary layer, it gets assigned the velocity from this velocity volume. If the apply boundary velocity is turned off, it then interpolates the velocity from its neighboring particles. So by having this on over time, it constantly says these particles should get closer and closer to matching the velocity volume, and it may not directly have all the velocity because some particles from outside of the boundary layer could flow in, but new particles that get created do get assigned the velocity volume. And at the actual strict boundaries, it applies the velocity volume onto it. So that is strictly enforced. The volume inside the padding is semi-enforced when this is turned on, and then completely not enforced at all if this is turned off. But again, at the volume limits, the velocity volume is always applied. And that's really what gives us the majority of the control. This is something that you could use if you want it to be more consistent with the boundary, but it's what is essential is having the volume limits itself. Okay, so at this point, we've set up our geometry inside the river. We have the collision volume to keep everything in the river. We've wired in our volume velocity, so it's going to flow in the x direction. It's going to come in and leave here, just the same as we saw before with particles being able to leave the simulation or flow back in. The level on either side is going to be maintained by the surface volume, and it's going to be maintained within a 4-meter padding on either side. One last thing, we initialize this with a velocity right out of the flip object, giving it the same matching velocity from the velocity volume. You could directly add in a particle field that has velocity on it if you wanted to, but this is an easy way to achieve this effect. All right, so that's basically it. That's how you create a short river. There's nothing too complicated with this. It's using the boundary layer quite simply, and we're able to get a continuously flowing river in doing so. Okay, so let's take a look at the river as it starts to bake in. So the initial velocity was just simply in the x direction, right? That's okay, but over time that's not going to be sufficient. But we see that we actually get a nice looking river flow taking fold here. Get some turbulence going along here. This is great. The overall flow is relatively steady because we've been able to control how much we input, and we're able to control how fast things actually flow out of our simulation too, which is really, really valuable. That's something that you couldn't have done before, and people just leave the river open-ended here and let it flow out. But that really affects the overall simulation. We want to make sure that we have a steady flow through the whole region here. We don't want to have part of this just sort of flow out the back end. We can plug both ends by setting up this boundary layer. And what really is valuable and powerful about this tool is that now that we have a relatively nice looking river going on here, a couple million particles, we can come back in and just chunk out a small region and up-res this, because we've been able to simulate this part and we have the ability to enforce velocity at the volume limits. We can enforce the geometry at the volume limits. We have everything we need from this simulation to come back in and control a small area and up-res it and potentially change what's going on inside the actual simulation. Okay, so now that we have our full river simulated, we may want to go in and change things up. Like say, for example, we have a shot here and we want to add a flipping torus through our river. Now, we're zoomed in quite a bit compared to the overall river, and we want to get much higher resolution detail in this section, but we don't necessarily want to simulate the entire river. If you can imagine, by zooming out, that's a huge amount of river that is just not captured at all in the shot. So if we increase the resolution here, we would have to increase the resolution of the entire river, and that can become very costly, and we may not want to do that. So by using the boundary layer, we're able to get around this problem by loading in the previously baked out geometry. So the surface volume of the full river and the velocity volume of the full river. We can bring that into this simulation and set our new boundary layer as those volumes. So in the source fluid here, we do that. We bring that information in, and we do it through this file SOP here, which wires up to the geometry that got baked out from the previous simulation. We apply blast here so that we make sure we only have the surface come through for the surface and the velocity terms come in for the velocity. And so we can wire these in directly to the flip solver in the boundary layer section. Also, we need the initial particles to wire into the flip object. So we do a simple Poincare volume and then volume sample in the wrangle here to get the velocity onto the particles, and we can wire this in. Before we brought in just the surface SOP, but in this case we want to have the initial velocities as well, because that will allow us to get away with less pre-roll. Okay, let's dive right into the DOP network. In the flip object here, we've wired in the initial particles, and we have the input type as particle field. So that's going to bring in the particles and the velocity on the particles, which is nice because we can start off with the right velocity. Okay, in the flip solver here, we've decreased the padding a little bit. That's because we've increased the resolution, so we don't need the padding to be nearly as thick. So 2 meters with an increase in resolution ends up being about as many voxels. The surface volume here, instead of being the flat object, like I said, there's this reference surface, a reference velocity. So the incoming geometry from each particular frame from the full river. So we should see the flow into this simulation matching the flow rate of the original river, because what's actually being fed into us is that information. So this concern about matching appearance and matching flow should be addressed by wiring in this into the boundary layer. So let's see an example of this. So in this flipbook example, we ended up zooming out the shot a bit to sort of make it clear where the boundaries were for the inflow and outflow padding of the boundary layer. You wouldn't want to actually capture that shot in reality, but for demonstration purposes, it's good to be able to see this here. So this simulation has about 12 million particles, whereas the full river in the previous example had a couple million particles. This is quite a bit higher resolution, and we're able to interact with the torus here as it splashes around, and we see very high resolution detail around the splashes that just wouldn't have been able to be captured in the previous example. We see that yes, indeed, we can actually resim this river. This looks quite nice. We get a continuous flow as we just quickly scrub through here. We see the turbulence along the side of the river. We get this continuous flow through here. We get turbulence of the inflow here, which is what we wanted to achieve by wiring in our pre-baked lower res river. We see very high resolution splashes throughout here. And this gives us a nice high resolution piece of our river. We do see a small amount of the boundary here. We see a sliver, but this is hard to avoid because this torus really changes things by splashing around and by blocking part of the flow. It's not going to match exactly, and it's going to be very difficult to try and get this to match, especially if you go and change things substantially in the shot. But what it does do very nicely is it controls how much of this fluid flows out of our simulation. Because we can enforce at the wall the velocity, we can limit the degree to which this is just going to flow out. If we didn't have this here at all, a lot of this water would just rush through and we wouldn't be able to control that. So yes, although some of the seam shows up, it's not dramatic enough that it can't be cut out of a shot. And so this is quite a valuable tool in that we can plug the front of this simulation with inflow, and we can plug the end of this simulation with outflow, and we can resim in this area quite nicely with a splashing object. And without, of course, the penalty of having to go and do the full river. Of course, there's a natural question. If this is a straight river, what if I wanted to have a bent river? And that becomes a bit more tricky because the boundary layer is naturally meant to be applied directly at the walls of this fluid simulation, and the volume limits of the fluid simulation are inherently a box. If we wanted to do something tricky like having a bent river, we would have to do something more complicated, and I'll get into that next. In Houdini 16, we greatly improved our surface tension effect, and it allows us to do things like create crown splashes, and it even is the driver for the suction fluid. But before we get into some of the more exotic effects that we can achieve, let's focus first on what exactly surface tension is. So if I turn this box here into a flip object and decrease the particle separation, perfect. I have a nice little fluidy box, and I'm going to make this just float in the air. And run this, nothing magical happens. We get a bit of receding, but there's really nothing there because there's no forces acting on the box. But surface tension is a force that acts on a fluid object based on how quickly the curvature changes. So, for example, the box here at the corners and the edges have a strong curvature change, whereas a sphere, for example, is constant curvature over the whole area. So a sphere shouldn't experience any surface tension forces at all, based on the fact that there's no curvature change. But our box, for example, does have some quick changes, and so we would expect to see some forces on here if we enabled surface tension. So let's do that. We go into our flip solver, volume motion. We've added this surface tension tab here. And click enable surface tension. And this value might be not strong enough exactly to get the effect we want, so let's turn it up a little bit more. And indeed, we see something happening to our box now. Sorry, let's rewind that. And our box has these sharp corners, like I mentioned, that get pulled inwards as the surface tension forces act. So all these corners you saw here, they all get pulled inwards. And as they get pulled inwards, the flat parts of the box actually get pushed outward. So let's rewind that again. The flat section here that doesn't have any curvature, that shouldn't experience any forces, ends up actually getting pushed out. That's because the surface tension force at the corners here pull in, and the pressure projection inside the flip solver says, I can't shrink my volume. I need to maintain volume somehow, so I have to push out in other ways. So these faces here that don't have any inward surface tension force end up getting an outward pressure force. And so they get pushed out. And so you actually end up with a sort of an opposite of the box, which forms this diamond. So every corner that gets formed now was a flat face in the box. And then those, of course, have forces that now pull it in because there's a curvature change, and we get close to our original box shape as a result. So we end up with this ripple back and forth. And this is all caused by the surface tension forces. But so for a box, it's kind of unrealistic. You would never really see this in a real situation. But it does this nice sort of ripple back and forth. And this can end up creating really cool effects when you end up getting ripples along the surface of a droplet, for example. So this also plays a key factor in creating something like a crown splash, which I'll get into next. Okay, so this setup is very similar to the waterline example that I showed before. The only difference is that I've enabled surface tension. So here I've enabled surface tension. I've changed the splashy kernel to swirly kernel. This does a better job at having nice flat and smooth surfaces as a crown splash is created. It's not as noisy and turbulent, and so it's preferred to have the swirly kernel activated. And I've also decreased the particle separation. And one thing that might be valuable is to actually decrease the grid scale here. You might find that the effect you get is a little sharper. It totally depends on the effect you're looking for. If you want sort of a more bulky, fat crown splash or a thinner, more spread out crown splash, the grid scale can have an impact there as well. And one thing that's really important to note is surface tension can have stability issues. It is possible that stuff in your simulation moves too quickly for the resolution. And if you start to see things look really turbulent and unstable, you might want to consider going to the substep tab and changing the minimum substeps to something quite a bit larger. This very likely is a place that can solve a lot of headaches for very small scale simulations where the stability starts to become an issue. So let's just run this example here and see what we get. Now this has the same downward velocity as the waterline example, but the splash does not come up nearly as high. And this is due to the surface tension strength. It pulls down as this splash is forming because, as I showed in the box, there's opposing forces when you have sharp features with a large change in curvature. So this splash here starts to fold outwards, and we get this thickened brim around the top, which is what you'd want from a crown splash. We have nice ridges that are forming, which is also nice, that something you'd like to get in a crown splash. So this is a good starting point. Certainly not a finished example, but very easy starting point to create a crown splash. And this can definitely be pushed a lot further with much higher resolution examples, which I'll show you next. So this is a much higher resolution version of a crown splash. The particle separation here is quite a bit lower, and we're really able to achieve nice results through this. We see the thickening up of the brim, so you can really achieve nice features through this method. As I pointed out before, we have the thickening around the rim, which is what you tend to see with crown splashes. We have droplets forming and shooting off. We have a nice we have a nice smooth sheet that forms that shoots out. And some of the droplets here have very nice ripples on them. For example, this oscillating droplet here. We get the single splash in the middle that forms, and a droplet comes out of there as well. Right, so with a simple addition in the flip solver, by activating the surface tension, you can create these effects quite easily. It may require a little bit of tuning, some of these parameters to get the right look, but the way the surface tension is handled in the flip solver should set you up nicely to get quality shots like the crown splash that I demonstrated. If you do find that some parts of your surface tension simulation get a bit noisy, we've added this blur here so you can globally blur some of the area, so this will smooth out the change in curvature if you notice that you have too much turbulence. If you have a location of too much turbulence, but you otherwise want to leave the rest of the simulation untouched, you can apply a mask here that only blurs in certain regions. So it gives you a lot more control over how the simulation is handled and where you may want to clean up certain parts that may look too turbulent and other places that are nice and smooth. So to assist you in setting up a crown splash, we created a shelf tool here, Crown Splash Particle Fluid, which sets everything up for you. It does it in a way that's higher resolution than this to achieve a nice result and a very good starting point to maybe move into a very high resolution simulation. But these are good starting points with all the settings pre-tuned for you to use. So this is an example of the Crown Splash shelf tool. The size of the splash is quite a bit more dramatic than the previous example, and that has to do with the downward velocity of the droplet, the surface tension strength, and the size of the pool. Those are all factors that play into the overall appearance of the crown splash. But in this case, we definitely see that there are thickening regions around the tip of the crown. We do have the nice ridges that we expect to see, and tendrils forming that will break off to create droplets. Depending on the look that you're going for, it's up to you whether you want to have a much more thick and shorter splash. This is totally a sort of a parameter tuning example. The surface tension strength that I had relative to what was going on in the previous example definitely was the reason behind why we saw the splash only coming up to a very small amount. We've also added another feature in the shelf tool to use the surface tension model, and this is this drip particle fluid. So the surface tension is nice for crown splashes, but it's also useful to make sort of faucet-like drip behavior. So in this case, we have just a sphere set up as an emitter through the source volume here, and surface tension enabled. And the surface tension is strong enough that it prevents this droplet from really just falling downwards. If we turn this off, we would see just a stream straight down. But the surface tension doesn't allow that to happen, and it pulls back and forms this droplet. So it's fighting against gravity. At some point, it gets heavy enough that it starts to break free, and we eventually see a bifurcation. So at this point, we notice that there's a pinching off that's about to happen and a topology change here, where this tip is going to be pulled back because the surface tension wants to correct for that curvature there, and breaks apart, and we end up with this droplet being completely separated from the rest of the stream. And as this droplet starts to fall, we notice that there are some ripple motions that occur within the droplet itself. And this is very similar to the box example that I showed before, where we end up with droplets that have rippling that is caused from surface tension. The simulation continues on, and droplets start to form as the surface tension pulls apart and creates these individual pieces. So depending on what type of effect you're looking for, the speed at which particles come out of the emitter will have an impact. The strength of the surface tension will have an impact on how things break apart. Even setting the grid scale can actually have an impact on when these parts pinch off, because the particles that are inside of a particular voxel form the surface, and the surface is what is computed for the curvature. So all these things are tied together, and these are parameters that you can play with to try and achieve the particular effect that you're looking for. One thing that's worth noting that is in the drip particle fluid and the crown splash particle fluid shelf tools is that we've changed gravity. We've reduced the strength of gravity so that we can get a slow-moving, small-scale effect for the simulation. We've also gone in and changed the substeps as well. So in this case, I have the minimum of 5 substeps and a maximum of 6 substeps. This is important to maintain stability. If I were to reduce the substeps, I would quickly find that this fast-moving droplet moving downwards here becomes unstable when these parts break off. And that is not going to achieve the effect that we want, so we need to increase these substeps. If you wanted to achieve something even smaller scale, for example, if you wanted to reduce the size of this emitting sphere here, and then correspondingly reduce the particle separation, you would find that it gets unstable quickly, and you'll need to increase the substeps as a result. This is largely due to the fact that surface tension has these instability problems built into it, and typically surface tension examples are done at a small scale. So it tends to be costly, and it tends to require a lot of substeps to be able to get the right look, unfortunately. But the wonderful thing about surface tension is not only that you can do the crown splash or this drip simulation, but it even extends to things that aren't even necessarily physical phenomena. The actual implementation of surface tension has led us to this really interesting phenomena that we created here called the suction fluid. So let's get into that. So the suction fluid feature that we've added to Houdini 16 extends from the surface tension implementation that we added. And it's a pretty simple concept. The idea is that the surface of the fluid here that we have is a certain distance away from this target object. So maybe at the bottom of this object, it's half a meter away or so. And the amount of distance that it's away is the replacement force for surface tension. So instead of the curvature that we discussed before, the force that we apply, or really it's the pressure at the surface, but we can think of it as a force, is how far away the surface is to the object. And that drives the fluid towards the object. So to use the shelf tool that we've added, simply click on that, click on the object, press enter, and then select the flip fluid we want to apply this to, and it drops down a few nodes. So the main parts are this anti-gravity node here, which is designed to oppose gravity, thus the name anti-gravity. The idea is that around the object, we don't want to have gravity pulling the fluid down if we want the suction force to be pulling the fluid up. We could increase the suction force to just completely overwhelm gravity and not have that have any effect just because the suction force is very strong. But that starts to become unstable. We get a lot of oscillations and it doesn't look very nice. So to get around that, we simply have this anti-gravity force that is applied in this outside distance area. So particles that are inside the object should encounter no gravity at all based on what this anti-gravity force is, and particles that are outside should experience a ramp of gravity that starts to apply less and less as you get closer to the object. And this is all highlighted in this Vex code here, but it's easier to interact with the parameter panel here. And additionally, as the object moves, we've linked in the velocity of the object here. We apply a drag so that we can try and move the particles along with it when the particles get pulled up into the object. So how do we actually get it there? We apply this suction force. And essentially, with this wrangle code here, it applies, like I mentioned before, the distance between the fluid surface and the target object. And that is multiplied by the suction strength, and it is ramped higher depending on where or how close it is and what the outside distance is. So for example, if you're 1 world unit away, so in this case, if you're 1 meter away, you will have 0 actual force. And if you're much closer, you will have the true distance times the suction strength and the ramp from the outside distance to the inside distance. Basically, you can think of it as the particle gets closer to the character, it's getting pulled further and further in. We want to have a ramp that increases the strength because we don't want to have a sudden jump at some distance, some outside distance away. We want to have a nice steady transition of the suction force as the object gets closer, as the surface is closer and closer to the character. So for example, some place out over here may experience a very, very light amount of force, and some location closer will experience a stronger force. Even though technically it's closer, the distance is less, and so the strength should be less. Because of that ramp, we get a nice gradual transition. And we'll see that when we run the example in a second. So what is this object? It's just our rubber toy with some animated transform. Let's just turn this off. And it just simply lifts up and moves around a little bit. Nothing too fancy, but enough to show you that we can animate an object and pull the fluid along with it. So when we use our shelf tool, we get the nodes put down in the flip solver, but we also get nodes put down in the geometry as well. So in this case, we have this collision source that gets put down. So one thing that's really important to keep in mind and be aware of using this tool is when the collision source is laid down, the voxel size is created based on the particle separation and the grid scale in the flip object in the dot network, but it's not directly tied to it. So if I increase the resolution of my simulation, this voxel size is not going to change. And if I maybe don't have a high enough resolution to really represent my character, which in this case I just barely do, it's just barely visible as a rubber toy, you may not achieve the look you want. So it's really important to keep an eye on this voxel size and how that relates to the quality of your simulation, because even if you increase the resolution of your simulation, if you don't increase the resolution of your target object here, you're not going to be able to represent it very well. And additionally, the exterior band and interior band are directly tied to inside distance and outside distance. So if you decrease your inside or outside distance by a lot, you will not have a large narrow band for your volume to actually represent your object. In fact, if you set it to 0, you could end up with some issues where you don't even have a narrow band at all for exterior or interior, and that could cause problems. So it's important to keep an eye on this as well. Okay, so let's just jump right in and activate this. So from just simply dropping the shelf tool down with the selected objects, we get fluid pulled up into our rubber toy. That's pretty cool. It looks all right from the beginning. It comes up and fills the shape of the object. In fact, if we look at the surface, it's a bit blobby, but it has the overall shape of the rubber toy. Okay, so I want to just change this here so I can see our toy and not look at the voxelization of it. So if we just run this again, we notice that there is quite a big bulge outside of the actual rubber toy itself, right? There's quite a big area around it. And this has a lot to do with the outside distance and how we set this outside distance. So it's good to have a big outside distance initially to pull everything up. For example, like this character does not sit directly on the water, so if you had a small outside distance, you may not actually be able to pull anything up at all. So we may want to change this. In fact, it's probably a good idea to keyframe this. So we want to keyframe the outside distance. This way we can control for the amount of fluid that gets pulled in and how far away it is from our character. So in the beginning, we want to keep the sort of bigger bulge that we saw, but we want to transition this gradually over time. So for example, this far out, we may want to set our outside distance to be something smaller, like for example, 0.3, which happens to be a voxel and a half. So if we look at the flip tank, particle separation is 0.1 and our grid scale is 0.2. So our underlying voxel size is 0.2. And so our outside distance transitions to be 0.3 around the 120 frames. So that will allow us to maintain the fluid tightly to the character and not have that bulge that we saw. And now because the character is going to move around through the scene, we may want to increase our suction strength. So although 12,000 is good in the beginning and that pulls up the fluid, as the fluid moves around, we want to have something stronger that's going to pull it in and maintain it as the character moves. Because as it moves, we may see particles fall off from our character. So again, we'll set a keyframe. And we'll set this to something much stronger, like 48,000. Now let's see how this works. So we see that the fluid gets pulled up into the character and creates a much tighter representation, where in the beginning we get this big bulge, which is quite a bit further away. We do see that our values are starting to change here. As the outside distance starts to thin out, we get a thinner representation of the character. By the time we get around the 120 mark, we see that this is a pretty good representation. If we surface this, we can see the contours of the character quite well. We can see the legs here and the formation of the tail, and even the contour of the head. We can't get the sharper details of like the horns, for example, but that's simply because we don't have the resolution in this simulation to achieve that. If you recall, the VDB volume of the character just isn't even at that level. If we increase the resolution, we would expect to be able to maintain those contours as well. But overall, this is pretty good. We get the shape of the character that we wanted, and we have a much tighter representation than before, and the character can also move about the scene. Now, as our rubber toy moves, we see that the particles are oscillating around and moving about inside the character, which is great because we want it to look like a fluid simulation, but we also want it to be driven to match our character. And so by setting our target through the surface pressure, we can maintain that fluid simulation appearance while being able to direct where the fluid goes. Now, as the rubber toy moves, we do see that particles fall off. And this is partly due to the fact that the rubber toy is moving quick enough that the outside distance doesn't grab the particles. But it's still a nice feature having it fall off and looking fluidy. And so having the stronger suction strength helps keep some of these particles in the rubber toy. Even though we have some particles fall off, it conforms to the shape as the rubber toy moves about the scene. And this can be taken much further and be used for substantially higher resolution simulation. So as an example of something that's achievable with a suction force in a much higher resolution, we had a model skull that is used as a suction force object. And it pulls this chocolate fluid up and forms the shape of the skull. And it does a pretty good job, especially if you consider that the jaw here is quite thin. The actual bone in the jaw is not really thick at all. And we're still able to fill the fluid into that space, and you get the right contours of the skull here. And really what's the most impressive of this whole thing is that it's not just directable liquids. It's not just directable particles. It's a true fluid simulation. There are ripples that occur on the surface of the skull. Even in the jaw, things are rippling around because it really truly is a fluid simulation that is just being sort of guided by this pressure. And this can be taken even further. So Jason from Black Ginger provided us with this really cool example of the suction fluid with these zombies climbing out of the river here and pulling up the water with them and moving forward. And as they do, the particles are sloshing around and falling off of them, but following the motion. I mean, the nice part is that there's this animated example of sort of what is possible. And yet, the dripping particles that are coming off the character really provide this nice and rich detail. In Houdini 16, we also made improvements to the viscosity solver. We improved the way that the fluid interacts with the solid at the boundaries so that slower moving flow gets smoother contact with the solid boundary. We also changed the way that it contacts in terms of how much it can slip. So in this example here, this viscous puck is going to fall on this rod, and the rod isn't going to spin around and fling the puck. Of course, the puck is sticky, and it's going to stick to the rod and only pull away when there's enough momentum to sort of overcome the stickiness. And we see, well, even so, there's still some parts that stay stuck to the rod. A lot of the momentum or the energy is lost because of this viscous connection here, and it slinks down to the ground. I think it's a pretty cool simulation, but there's no control for the artist to determine how sticky or how slippery this thing should be. And we wanted to provide that type of control. So we added this slip-on collision option. And in this example, it's activated, and the slip scale is set to 0.75. So that means it biases towards the velocity between the fluid and the collision, taking the fluid's velocity and not the collision's velocity. If the slip scale is 0, then the fluid receives the velocity from the collision, which means that it can't slip. And then if the slip scale is 1, then the collision doesn't apply any of its own velocity to the fluid, at least tangentially. In the normal, it's still applied, but tangentially, the fluid can freely slide back and forth. So as this puck starts to get flung by the rod, the momentum of the puck creates this slip. You see here it starts to form. This puck is starting to slide off of the rod by this at the contact point, and it's not grabbing nearly as much as the previous example because of this slip scale. So we've actually seen that a decent amount of this puck is actually slid off the rod now, and this was not the case in the previous example. And the way that the puck comes off here is just completely different, right? It starts to slide off and then gets flung. So let's play that back the whole way. Right, so allowing this puck to slide along the rod gives us this effect that we wouldn't have been able to achieve before. We would have been stuck with, well, I think it's still a cool example, but we would have been stuck with this example. We would have not been able to do something different. Now that we've added this slip-on collision option, there's a lot more control for the artist. So At the moment, this is just a global scale here. This just completely sets how the velocity behaves at the contact of the collision. In fact, inside of the mechanics here, it's just the opposite of the gas stick-on collision, which you may be familiar with in the collision tab. There's a stick-on collision here. What's important to notice is that for a normal viscosity-free fluid simulation, so if this was completely turned off, it's just a typical fluid simulation, we have what's called a free slip condition, which means that the fluid is allowed to move tangentially along the collision object without getting any of the collision object's tangential velocity influenced into it. When you turn viscosity on, we have the opposite issue, where it's a no-slip condition, which says that the tangential velocity of the fluid should match exactly to the tangential velocity of the collision, which is what we saw in the initial puck case, where if we go back here and watch, there is no sliding at all. At no point is the puck sliding along the object. It's only once the object finally stops that the puck begins to detach due to the momentum of the fluid. So that's why it's important to have this slip-on collision here in the viscosity tab, just like it's important to have the stick-on collision in the collision tab, because in this case, for a viscosity-free solution, it gives people the ability to control what otherwise would be free slip condition. You can change that by modifying this. For viscosity, we want to have the opposite. We want to be able to control what would otherwise be a no-slip condition. And that's why we've added this here. So even moving beyond that, we now also have a control field. So maybe you want to have a specific region that is more slippery than another region, where I said in this case, it's just a global scale. But it's possible that we may want to have the slip just completely dependent on like maybe temperature or some other parameter. So in this example here, I have just a simple box that I've turned into a fluid that's going to splash down on this ground plane. And it has some viscosity, 500 for example, and viscosity is enabled here. We have slip-on collision activated, so this should just be a full slip, and if we run it, indeed it hits the ground plane and slides down and just keeps sliding. If we bounce this back and just turn this off completely, we would expect this to have a very, very, very small flow, if any at all. And indeed, we see that the flow is just completely just wiped out pretty early on, as all the particles stick once they sort of spread out. So there's a very, very thin layer, and the fluid is just basically completely attached to the ground plane. Okay, so that was all or nothing. That was just a global control. So we've added on the volume tab here, or on the volume input here, we've added a slip field, which if we visualize, is varying from left to right. So on the left side, we have a value of 0, and on the right side, we have a value of 1. And that gets passed into here, so we can use our slip field, because it's been created at the volume input, and activate this control field. So let's just turn this off. And let's run this again. So pretty quickly we notice that on the left-hand side, this is gripping just like we saw before, right? Where it spreads out, and pretty quickly on, it loses all of its velocity and just sticks. But on the right-hand side, this is continuing to flow. And this is what we would have expected, right? So like I said, when we showed the plane here, on the left-hand side, this is 0, and on the right-hand side, this is 1. And this is how we set it up through a simple wrangle, and even the guide range clearly indicates that 0 and 1 is the varying colors here. So this gives you the ability to control areas that you might want to have greater slip and areas where you might want to have more of a stick. And this control now is available and allows you to do a lot more with viscous fluids than you were able to do before. I want to thank you for taking the time to watch this masterclass. If you have any questions or comments, please feel free to leave a post below or in the side effects forum, and I'll do my best to answer. Thank you.